15.2 indicator electrodes. In the previous section, we looked at our reference electrodes. How do we make them? How do we make a reading with them? Making sure that we know to adjust the reading of our measurement by subtracting whatever that voltage is for our appropriate to that reference electrode. Now we're going to look at the other side. How are we going to do an indicator electrode? What's going on with the actual measurement part of things? So we got three different types of indicator electrodes. The first one is called a simple method, a simple metal. We're just going to take, it's sometimes called an indicator of the first kind. We're just going to take our metal and we're going to put it in a solution of its ions. We then have a glass or liquid membrane and an enzyme electrode. These guys are all in one kind of group where we're going to do kind of the same trick each and every time. So that's one group. And then over here, these guys are going to form a third kind of electrodes. So our gas sensing and our solid state electrodes are going to rely on a slightly different trick to get the voltages down. You are going to need a reference electrode because to make a potential measurement requires that you have 2 points. Right? So let's look at our indicator electrodes. Right? We're going to have metal and ion selective, and then our gas sensing ones over there. So our metal electrodes, which are shown here, you're just going to develop an electric potential in response to a redox reaction at a metal surface. So this is those same sort of 2 electrode cells that you saw before. Now, some of you might be wondering, which one is the anode and which one is the cathode, right? The reduction happens at the cathode. So when you've got a reference electrode, it might be the anode, it might be the cathode. It kind of depends on what the other working electrode is going to be. So we've got to make a measurement. We've got a reference electrode in here. And you can see that you've got this little plug down here at the bottom. That's going to be our salt bridge. Then you have a solution of Ag+, and you've got Ag wire in here. So this is very much like in lab when you did station 6, where you made the silver bromide solution, and then you had Ag and AgNO3. Right? This is very much like that setup. Right? This is going to be, instead of having a plug down there, you had a little plug that was sitting in a beaker with some potassium nitrate or sodium nitrate or something that was going to allow those ions to flow. So here you're just going to have this one salt bridge that's going to maintain our charge neutrality. Ion selective electrodes, we're going to talk about later. They're going to bind one type of ion to a membrane that generates an electric potential. That membrane can be lots of different things. It could be glass, like in a pH electrode. It could be a polymer, like it could be with enzyme electrodes. We'll talk about those in a second. So let's look at our simple metal electrode. We have bare metal in a solution of its cation. So we're going to take a chunk of silver and we're going to embed it into a Teflon body, and then we're going to have some just plain wire coming out this way. The reason why we do want to do this is that you're going to use a minimum amount of silver down here, and then this wire can just be like plain old ordinary steel or copper wire, because all it's got to do is conduct electrons. All of the chemistry is going to happen at the surface of that electrode. So, you want a little bit in there so you can polish it up, and you're not just going to completely wear it down, but you want to use a minimum amount. Right? This guy's going to be called our indicating or working electrode. And the equation for that is we've got some metal, and it's got a charge to it, and it's going to pick up a corresponding number of electrons, and we're going to make a solid at the other end. So when we do that, we're going to have a Nernst equation that's going to dictate that potential, and it's going to say that our indicating electrode's potential is going to be our E cell minus 0.0592 over N times the log of 1 over the metal concentration. So notice that this guy is forming a solid, which means it's not going to show up in our equilibrium expression. Really, we should probably do something like this, where it's raised to the number of electrons power, right? So we might need to, or whatever the stoichiometric coefficient is, raised to the m power or something. So we might need to raise that to some exponent. All right, so where are we going to get that? So the voltage on our silver sensing electrode, we're going to look at our indicator voltage is going to be our 0.99 volt, 0.799 volts that we're going to get from our table, right? That's from our table of E naughts. Right, that's our table value. And we're going to do 0.0592 over 1, because it's a 1 electron process, times 1 over the concentration of Ag. So we can take this minus term, right, minus and a log, and we can throw that into a P function, right? So we're going to have 0.79 volts minus 0.0592 volts times P of Ag. If we use saturated calomel electrode as the reference, that is the other half reaction, right? That's going to go into our E naught cell. Right? If we had used a silver chloride reference, it would be a slightly different number in there. Right? So our E cell is going to be our indicated voltage minus our saturated calomel electrode voltage. So we can rewrite this and redo this equation so that we can get PAG. Now remember, this PAG is minus the base 10 log of the activity of the silver, right? Which means this is really measuring the concentration indirectly, just like a pH meter is going to measure the concentration of H+ in solution. So our PAG is going to be related to our overall voltage, right? The voltage that we measure, at minus, sorry, our point to be related to the voltage that is coming from the table, the 0.799 volts, minus 0.244 volts, minus E cell, which is what we're going to measure, and divided by 0.0592. So all we're doing is we're rearranging that Nernst equation. All right, so let's do an example. We got a silver wire, and we're going to dip it into a silver nitrate solution, and we're going to make a potential of 0.45 volts measured versus saturated calomel electrode. What is the concentration of Ag for the unknown solution? I'm just going to draw this out for us real quick. Now we're going to have our saturated calomel electrode over here. We're going to have our Ag wire over here. We're going to have a solution of Ag in here. We've got our salt bridge that's in there. Remember that our saturated calomel electrode is going to constantly be generating this 0.244 volts. We're going to have this overall reaction, and then we're going to look at our E cell that we've measured up here. All right, so our PAG, we measured 0.54 volts. So 0.54 volts goes in our measurement. And this is coming from our saturated calomel electrode. That's our overall reaction. So our PAG is going to be 1.791, which if we want to convert that into a concentration of silver, we're just going to do concentration of silver is 10 to the PAG, which is going to be 1.62 times 10 to the minus 2 molar, right? Pretty easy equation for us to manage. Would you expect to be able to do something like that on an exam? Of course you would. Right? Our simple metal electrodes are also sensitive to the anions that form low solubility precipitates with the cations. Right? So what's neat is we're not just able to measure the cations that correspond to the metal wire we're sticking in there. If that forms a precipitate, and that precipitate is not very soluble, we can kind of backdoor what the concentration of that anion is instead. So if I wanted to make a probe that was sensitive to chloride with a silver electrode, right? We're not going to measure chloride directly. We're going to measure it indirectly by looking at how much Ag is left in that solution. So if I take silver chloride, it's going to dissociate a little bit into Ag plus and Cl minus. And my Ag plus can pick up an electron and form Ag solid. Therefore, if we take an electron and some Ag chloride, silver chloride, we can make silver solid and Cl minus. All right. So we're going to round about our way to get there. All right. So if I've got my expression for our voltage for AgCl, it's going to be our E naught for our silver minus 0.0592 over 1, because it's still a 1 electron process. And then we're going to do the log of the chloride divided by the Ksp for the silver chloride. Right? We're going to substitute in the Cl over Ksp for the Ag, because our Ksp value is going to be Ag times Cl. So all we're doing is we're taking our Ksp, rearranging it so that we're going to replace our 1 over Ag that we had before into Cl minus over Ksp. Once we do that, we can put that back up onto our equation, and we'll get that our E naught for AgCl is equal to the E naught for Ag plus 0.0592 log Ksp plus 0.0592 times the P of the Cl minus. Right? So we're going to measure our indicated electrode. That's going to be our E naught for our AgCl times 0.0592 times the chloride ion concentration, 0.222 from our table, and PCl minus. So what we're really measuring isn't an increase in our chloride concentration, but a decrease in the silver ion concentration. Our PCl goes down as our PAG goes up, and vice versa. Right? And that's just looking at our common ion effect. If our ability to, if we've got more chloride in solution, we're going to have less silver in solution. Right? So you're measuring the decrease in silver rather than an increase in chlorine, because that K is going to remain constant. For some metals, a good electrode just cannot be made. So if I'm trying to measure sodium and I fix a big chunk of sodium into water, it's not going to do too well for us. Or if no metal is involved. So if, for example, if I've got iron going to iron 2 plus, right? Iron 2 plus isn't a solid. I can't make a solid electrode out of iron 2 plus. In that case, an inert indicating electrode like platinum could be used, something that's not going to react with stuff. Something like platinum, glassy carbon is a good inert electrode. This type of electrode only measures the ratio of the ions. It's not necessarily quantitative, but it is something we can use for a titration. So we're not going to really be able to quantitatively do this kind of stuff with a potentiometric measurement. There are other things you can do with amperometry that we might be able to do, but we'll look at those in the next chapter. So here is an important graph coming up. All right. So if we take a graph of our voltage on our indicator electrode, remember that's our guy on the right-hand side, that's our metal wire and its cation, and over here is P of X, where X is the concentration of our metal, we're going to get a nice graph that looks like this. The slope is going to be 0.0592 over N. The intercept is going to be the E naught value, right? So we can learn a lot of things by just measuring our voltage, systematically changing the concentration of whatever cation it is we're looking at, right? So we can learn E naught, which is an important thing to know. We can get the number of electrons, and we can get that constant 0.0592. And remember that constant 0.0592 rolls in a couple of different things, right? It's got that transition from a natural log to a base 10 log. But it also encodes Faraday's constant and R, our universal gas constant. So let's look at a quick example of potentiometry with an oscillating chemical reaction. Right? So we've got this oscillating chemical reaction with malonic acid reacting with bromate to form bromomalonic acid. It's going to go between yellow and clear. Right? This is called the Belousov-Jabotinsky reaction. It's a cerium catalyzed oxidation of malonic acid by bromate that oscillates between the yellow and colorless forms, because the catalytic process causes the quotient of cerium 3 plus to cerium 4 plus to oscillate by a factor of 10 to 100. Right? So we're going to set up a little power supply here. We've got a computer or recorder that's going to record things on the millivolt scale. We've got a saturated calomel electrode, and then we got this oscillating reaction that's happening in here. Now, because this oscillating reaction is going to bounce in between the cerium 4 and the cerium 3, we're going to see changes in the voltage as we've got different ratios of 3 plus to 4 plus. Right. So as your solution goes from colorless, it's going to have a low potential and then a higher potential as it goes to yellow, and it's oscillating, so it's bouncing back and forth between those. As the color oscillates, so too does the cell potential. Right? It happens over about about 3 a minute, so it's about every 20 seconds or so that it changes color. Right? Section 5.3. What is a junction potential? All right, so remember we said a potential is a measurement that we're going to make where we have two different things.